Good morning. So today I would like to discuss the different logics to realize the various gates. In the literature mainly you have two types of techniques. One is the gate logic and another one is switch logic. Coming to gate logic, the gate logic also called the restoring logic. It is based on the inverter, that is the basic circuit is the inverter, and with the gate logic you can easily realize the universal gates like NAND gates and NOR gates. But constructing the basic gates, basic gates like AND gates or OR gates needs more transistors in this gate logic. In this case, in NMOS technology, proper ZPU by ZPD ratio we have to maintain to get the symmetrical operation. That is 4:1 you have to maintain. But coming to switch logic, in the switch logic case, the basic one is using pass transistors or transmission gates. Okay, switch logic is based on pass transistors or transmission gates. The advantage of realizing using either pass transistors or a transmission gate is, especially with the pass transistors, the less number of transistors you can realize. No static current between the power supply rails, and you can easily implement AND and OR gates. But the pass transistor logic suffers with degradation of voltage levels because of the threshold voltage, and you can't drive more number of pass transistors with one another. If you use that one, the voltage at the logical levels may not satisfy. But to avoid these two drawbacks, the last 2 points are represents the drawbacks with reference to pass transistor logic. Those are avoided by using the transmission gates. If you use the transmission gates, you can avoid the voltage degradation problem because of the threshold voltage. So that with the transmission gate, you can reduce the voltage degradation problem. But the problem is the transmission, with reference to transmission gates, the complexity is more, so that more area it occupies. Fabrication problems you can get. To operate the transmission gate, true and complement control signals you need to have. Those are the problems with reference to transmission gate. First of all, let us see what is pass transistor, why the voltage degradation may occur in the pass transistor case, and how to realize the different gates or Boolean equations using pass transistor logic. So this slide representing the PMOS pass transistor and NMOS pass transistor action with reference to input signals, like applying the input signal. See the diagram. The first one is the NMOS pass transistor with the input is the transition 0 to 1. 0 is 0 volts, 1 is the 5 volts. Another one is PMOS transistor with the same transition 0 to 1 transition. 0 means 0 volts, logic 1 means 5 volts. That is applied at one end of the pass transistors. When they switched on the pass transistor, either NMOS transistor or PMOS transistor, when they switched on, what is pass transistor? The output, the other terminal, whatever the input you applied at one end, the same you can observe at the other end. With reference to NMOS technique, the output is logic low, that is 0 volts we are getting with reference to input logic 0 volts. But with reference to logic 1, the output is not exactly equal to the input voltage. Observe here, the output is only 4 volts instead of getting the 5 volts. This is why this will happen, means because of the threshold voltage of this transistor. So that means automatically here the threshold voltage is 1 volt. That's why 4 volts we are getting. Similarly, if you observe in the PMOS transistor, with reference to logic low, instead of getting 0 volts, we are getting 1 volt. But with reference to logic 1, exactly whatever the input voltage amount we have, the same amount we can get the output. So these are the voltage degradations. So that we can say easily the PMOS pass transistor is poor at logic 1 but good at logic 0 transmission, whereas PMOS transistor is poor at passage of logic 0 and good at passage of logic 1. Okay. Now let us see the realization of this pass transistor. This particular table is the truth table for the pass transistor. We can take AB are the inputs, suppose AB are the inputs and X is the output. Two input variables AB means 4 possibilities are there, 0, 0, 0, 1, 1, 0, 1, 1. Out of these two inputs, B input acts as a gate input. In this example, we are assuming B is the gate input. So based on the B value, whether the transistor is switched on or off decided. Let us see the first case, A0, B0. Since B is 0, the transistor in half mode. The transistor in half means there is isolation between A and X. That's why the X is at high impedance state. It is considered as a high impedance state because there is an open circuit between A and X. Let us take the second condition. A is 0, B1. B1 means the MOS transistor or pass transistor is switched on. When it is in on, whatever the voltage available at one end, the same you can get the other end. Okay. So since A is 0, X also 0. Similarly, if you take the another combination under two variable, A is 1, B is 0. Now B is 0, so that the transistor in the half mode, hence again X equal to Z. But with 1, 1 combination, because the transistor is in on state, the X equal to A, that equal to X equal to 1 here. So this is treated as the truth table for the given pass transistor. Okay. Now see the realization of logic circuits using pass transistors. The realization follows the Shannon's expansion theorem. The Shannon's expansion theorem is like this under two variable notation. The expansion, if you observe f of a comma b, means that is the function of two variables a, b. The expansion is like this: a dash b dash into g naught plus a dash b into g1 plus ab dash into g2 plus ab into g3. So 4 terms the expansion theorem consists, because two variables are there. Under two variables 4 possibilities are there. That's why 4 terms you can expect. With reference to this expansion theorem, the realization is like this. Here the realization is representing for the two variables like this. Okay, it is the circuit for the 4 to 1 multiplexer. 4 to 1 multiplexer. All the variables, all the two variables work as a gate control signals like this. whereas the four inputs are G0, G1, G2, G3. The first row in this, the first two transistors A0, B0, A dash, B dash realizes the term A dash, B dash, G0. Okay, that is the term realized by these two transistors, whereas the second term realized by these two transistors, third term realized by these two transistors A, B dash transistors, and the fourth term realized by these two transistors. Okay, this is the generalized realization for the using pass transistor logic. Suppose if you take the example like the function f equal to a dash b plus ab dash, a dash b plus ab dash. So with two variables, here also the function consists two variables, right? Two variables. But with the Shanon theorem, as per the Shanon theorem, the function should consist four terms. But the given function consists only two. Okay. So the other two terms are absent in this case. So with the other two, in the logic diagram, the transistors with reference to other two terms, for the other two terms the value is 0, the input value is 0, whereas the function consists the product terms like a dash b and ab dash. For the transistors which realizes these two terms, the input is VDD. Okay, because these two are the presented product terms, that's why VDD input is connected at the G place, whereas for other product terms which are absent, for them the G value is 0. Okay, so like that you can realize simply. But if the realization is like this, more number of transistors you can observe. If you see the minimized realization using pass transistor is, in the expression if you observe, both the variables with reference to both the variable, complement is available and true is available. Okay, a is true in one term and complement in another term, b also true in one term, b is complement in the other term. So generally the variable which is available in both and in both true and complement form, that is treated as a gate input, gate control input automatically. So here with the two transistors you can realize this function instead of using 8 transistors here. Let us see how it will be. This is the realization. Okay, so here in this case I am taking A as the gate control input. So A dash, for one transistor A is the gate control input, for other transistor A bar is the gate control input. With reference to A gate control transistor, automatically the input one end or input is B dash, since the product term is AB dash. Similarly, for the transistor with gate control is A dash, the input is B, as per the product term, like that. Okay, and the other end is the output, automatically the other end is the output. So this one is the called minimized pass transistor realization. Okay, following. Now let us see, suppose if the function is given like this, f equal to a plus b dash c. So realizing this function using pass transistors, how means, by the using Shanon's expansion principle, you can expand this function and you can realize. In the expansion case, whatever the variable you can take and expansion with reference to that variable. First of all, I am expanding this function with reference to A. Expanding means with reference to A, I have to show that variable A in both true and complement. Here the A is available only in the complement form, true form. Now I am including complement one as like this. Okay, so f equal to a into 1 plus the second term includes like a dash dot b dash c. Okay, since it is the first term is a into 1 is a plus the second term with reference to second term I am adding a dash into b dash c. Okay, so with reference to one variable the function is expanded. Now I have to expand the function with the another variable. Now I am taking b is the another variable. So if I expand with reference to b, the function becomes like this. So this is the b involved term. Let a bar as common of. So b dot 0 plus b dash c. So that it is totally equal to the original function f equal to a plus b dash c. So the expansion is you have to maintain up to the single variable existence. Okay, so the single variable in the not expanding form c. Now c. Okay, both a and b are in the expanded form, only c is available as not in the expanded form. Up to that level you have to do. Okay, after that the circuit connection is as usual based on the what I said, the variable which is available in true and complement, that is usually applied as a gate control input. Okay, so first of all see the bracket one which I am going to realize is using two transistors connected in parallel. Its gate voltages are b and b dash, whereas inputs are 0 and c. Okay, like this. That one is connected in series to another transistor, and the transistor is parallel to one more transistor. For this one, the transistor which is in series with the input a dash at the gate, and for the other transistor the gate is a and its input is VDD. Okay, so like that you can realize using pass transistors logic using Shannon's expansion theorem. Okay, are you following? So first you expand the given function with reference to all the variables up to single variable, that single variable no need to expand up to single variable. Okay, so here three variables are there in the original function. So therefore with reference to two variables I expanded the function, right? Here a dash, not a, here it is a dash. So like that the expansion can be done, and finally the diagram easily you can construct like this. Okay, clear? In the next class we can see what are the different logic families are there in the pass transistor logic again.